Here we begin our preview of repeated integrals. There's a lot going on this sheet of paper. There's a lot of examples on this sheet of paper, so I want to make sure it's clear and obvious what's going on here. We have this concept that's going to take our 2D integrals that find area and take it to 3D. But I want to take you back to this idea of summation. If I'm on a 2D graph and I have this nice curve and I'm taking the integral from a to b, remember the idea is that I have an infinite number of rectangles and I'm adding up the height at each one of these rectangles and infinitely small, barely changing, infinitesimal dx, and summing all of this, all those rectangles will result in the area of this. And that was a single integral. Now that we come to double integrals, it might be better to view it like this, as a series of 2D areas, these prisms that would shoot up all over that surface and fill in that volume to the best of its chunky rectangular prism ability. And so when I see this symbol, f of xy, it's creating some sheet, some blob over the top of my xy plane. Like here, I have a dum-dum wrapper. This dum-dum wrapper has curvature, it's a very irregular shape, and imagine trying to fill this with rectangles. It's not going to work nicely unless each of those rectangles' dimensions gets so small that it's basically a bunch of needles filling this of all various heights. And you say, well, how do I know what the height is? Well, underneath this dum-dum wrapper is an xy coordinate plane. And for any xy combination, it will output the height. So we have this symbol, f of xy equals some function, right? This one might be like 2 times the x plus 3 times the y squared gives me the height at any given point. And so then I would be integrating this function to then find the volume of this 3D blob. I'm basing it on the 2D plane. I'm grabbing again infinitely small rectangles, pulling up this rectangular prism to the height, the roof that is the dum-dum wrapper, counting that volume and moving on to the next one. And that's the idea here. When I'm doing these, it's like I'm getting a bunch of areas and pulling it across might be one way to view it. That would be if you're thinking in a case of dA. Generally, we might give you an integral that says blah, blah, blah dA. That's just the differential of this measure across that area. Sure. All right. So it's this idea of 2 sweeps will create 3 dimensions. As here, 1 sweep brought about 2-dimensional area. 2 sweeps along x and along y would produce something in the 3rd dimension. So you could also think of it as length times width times height, where that z function is height, my x and my y make up my length and width, and so I'm going to sum up and multiply all of the lengths times all of the widths times all of their individual heights to fill up all of those volumes, one prism at a time. Let's do some examples. Again, the goal here isn't just perfection, it isn't a full understanding of what's happening. It's a practice of the mechanic of a double integral. So 4 minutes of me talking about what it is already probably too much. Let's just crush examples. I see dy first. Come on, focus. I see dy first. Hello, hello. There it is. I see dy first, and so that means if this first integral goes off of my y bounds. If this is not containing a y, it should just be treated as a constant, meaning this becomes 2xy. Meaning this becomes 1/2 y squared. You know how to integrate. And I'm going to, this is my antiderivative. And so I have to evaluate this antiderivative from 1 to 3. And all of that will take place inside this dx block. I would get 0 to 2. I plug in my 3, I get 6x. I plug in my 3, I get 9/2. Don't forget the lower bound, minus 2x plus 1/2 dx. I simplify that down just a touch. 0 to 2, 4x plus 4 dx. And now we're just rolling. 2x squared plus 4x dx. I evaluate this. Oops, I'm sorry. I evaluate this from 0 to 2, and I get my final answer. 8 plus 8 is 16. Notice on the bounds how we wrote y equals and x equals. It's just safe. It's just being careful. Because if you're not paying close attention, you could mix them up. And here, if I plug these into y and these into x, or these into y and these into x, different things will come out. So I need to be very careful. Let's just run another double integral. The antiderivative here is negative cosine y. I'm going to evaluate that thing from 0 to pi, and all of that will be wrapped inside this dx integral. So first it's like I'm combining y and z. Then it's like I'm adding in an x element to then have x, y, z for a volume. Here we go. I'm evaluating this thing. I get, oh, that's a lot of negatives. Let me be careful. Antiderivative is 2x from -1 to 1 gives me 2 minus -2 is 4. Like it's really just, are you good at integrals? Please do it twice. Please keep your bounds in the right places. Please keep things in order, and just take the integral twice. Not rocket science, just 2 integrals. Now I have a triple integral, and you're probably saying, well, what's a 4th degree measure that this would give me? Again, I think this one is volume. We can understand that why later. It's that the fact that my integrand is 1 means this wrapper. Let's go back to our friend the dum-dum wrapper. What's happening here is, instead of having a 2D plane underneath it and setting the dum-dum wrapper on top, it's just visualizing this dum-dum wrapper as a 3-dimensional object. And then, for every moment, at its unique x, y, and z, it has its special measure. Now in this case the measure is 1, but let's think of something like gravity. What if this was a weird, terrible Earth? This was the shape of our globe, and I know that gravity is not the same across my globe. And so if I wanted to find out the total gravity of Earth, I would have to add up all of the gravities at all of the different locations. If this was a mass and I wanted to know the density of it, well, if I had a function that could tell me at each moment what the mass density was, because it's not consistent across the object, I would be adding up all of the mass densities across this 3-dimensional area and getting the total mass. What if this was a field and I just had some kind of magnetic pull? Well, the magnetic pull in this region is different depending on how close or far away I am from my magnets. Well, if I had a way to measure the force in x, y, z components, I could add up the total magnetic force by, again, filling this area with infinite skittles, and adding up the little magnetic forces for each skittle would result in the total magnetic force. That's how a triple integral is different than the rectangular prism double integral. Now we're just going to do some calculus. The antiderivative of 1 is just z. But notice my bounds on this one are not just numbers anymore, they are functions. Z evaluated from 0 to x plus y, dx, dy. It is important to keep these dx, dy's in order to make sure they match their bounds the whole way through. Everybody finds their own way to write these bounds when they do them. Again, not to get too sidetracked, 0 to 2, 0 to y of x plus y, dx, dy. Another antiderivative here lands me at 0 to 2. 1 half x squared plus xy from 0 to y. dy. Again, I have to keep carrying all of this stuff along or I might run into an issue. Again, another antiderivative, or evaluating this antiderivative here gives me from 0 to 2, it gives me 1 half y squared plus y squared minus zeros. So now I have 3 halves y squared dy. Again, one more integral here. 1 half y cubed from 0 to 2 gives me 8/3. Final answer. Oops, 8/3. What am I saying? 8 halves. Me done. Gives me 4. Right? I'm just integrating it, integrating. I'm using all my trig, I'm using all my power rules and all this kind of stuff. And so on the back we have some casting but forward of what some examples could look like in the future. Again, we have 4 integrals on this sheet. I'm going to kind of blaze through 4 integrals because again, it's just showing you, hey, if I want to find the volume under this plane over this region, magic happens and this integral pops out for you to solve today. In the future, you will learn these magic steps, but today we are just focused on, hey, can you do the double integral mechanic? You absolutely can. From 0 to 2, this antiderivative 4y minus xy minus 1 half y squared, evaluated from 0 to 1 dx, gives me 4 minus y. Oops, nope, minus x, my bad. See, you got to keep track of what you're plugging in for. This is from y equals 0 to y equals 1. 4 minus x minus 1 half. Yep, that sounds about right. Don't forget your dx. So now I've got from 0 to 2, 7 halves minus x dx, I get 7 halves x minus 1 half x squared from 0 to 2. Again, I'm plugging in 2 and I'm just getting, what is that? 7 minus 2 is 5. The volume is then 5 cubic units because I was finding volume under this plane over this region. Next, this object has a variable density and oh my gosh, this integral looks terrible. Anytime we have a square root, something yucky happens. I'm going to wave my magic wand one more time because we know that negative x squared minus y squared would make negative r squared from our polar knowledge. But that's not going to change my differential, and we're not going to tell you today how that differential changes. Just trust me today that dx, dy, or dy dx would turn into r times dr d theta. We'll discover that more into your February, March, April of the year, where the Jacobian does this. But for now, negative 2, that's also going to change my bounds in theta and r. Again, waving my magic wand from 0 to pi, 0 to 2, square root of 4 minus r squared, r dr d theta, like a pirate, r dr. Well, now I have an integral that I can solve, and I don't have to use trig sub as much as I'd love to. I have a u sub set up right here. U is 4 minus r squared. du is negative 2 r dr. Negative 1 half du is r dr. I also have to move my bounds with this guy. When r is 0, u is 4. When r is 2, u is 0. So I also end up with flipped bounds on this guy. So can we just agree that this is going to generate a negative 1 inside my integrand? This is going to generate a negative 1 half. And now I just have this. And my bounds reverted to 0 to 4. Right, that 4 to 0 flips to here. If you don't, just trust me that I did it correctly because I definitely did. Now I'm here, integral from 0 to pi. Antiderivative here is going to give me, what is that? 1 half times 2/3 u to the 3 halves. Evaluated from u equals 0 to u equals 4 d theta. Keep on keeping on. 0 to pi. This just turns into actually, right, 4 cubed 64 square root is 8/16 8/3 d theta. Well, that's a nice easy antiderivative. 8 pi over 3 for my final answer. Right, this just really starts rolling downhill once your integrals start to simplify. That first one, right, it took us 3/4 of the time to get this done, and the last 25 we're just running out of there. On to the next one. Iterated integrals are used when we find flux or flow through a surface. Imagine this amount represents the amount of flow of a liquid over this triangle. On this plane, over this region, with this function. Woo! Right? A lot going on. You can see how all of my bits and pieces show up, but we're going to ignore that for a moment. Let's simplify this integral before we get to it. I can already do an antiderivative here. 4y minus 2xy, almost off the page at this point, minus y squared, evaluated from 0 to 2 minus x dx. And this is the yucky step because I'm turning in 2 minus x, 2 minus x, 2 minus x. That next step when I get over to the left side is not very kind. Still this integral from x equals 0 to x equals minus 2 minus x squared dx. Now, you're just going to have to trust me on this next step. I've done some of the algebra in the background, multiplying all these out, combining all these like terms. I hope that you pause this and do it on your own. 0 to 2, x squared minus 4x plus 4 dx. Wow, that turned out so nice so quick. Yeah, like 2 steps here of just algebra simplifying. Take another antiderivative, 1/3 x cubed minus 2x squared plus 4x from 0 to 2. And again, plugging in that bound of 2, I get 8/3 minus 8 plus 8 is 8/3. That is the amount of flow over this location along this plane with this amount of, this defines the amount of flow for each skittle. Last one, extra yucky, we can power through here. This looks terrible. And in fact, these should probably all be rows. But regardless, first this is rho, then phi, then theta. When we do, eventually, when we talk more about spherical, it will always be this. What we're finding is, again, we have divergence. No comment about what divergence is today, but it will be this vector field across this hemisphere. The hemisphere helps set our bounds. This vector field helps set what's happening inside. And here we go. I'm going to simplify and combine my rows. This is 3 rho to the 4th sine squared phi. And so now I can start my antiderivatives. 0 to pi, 0 to pi over 2. This would be 3/5 rho to the 5th sine squared phi d theta. Don't forget to evaluate this one from 0 to 2. Plugging in that 2 here will give me 0 to 2 pi, 0 to pi over 2. I get 96 over 5. Woo! Sine squared phi d theta. Now I have another antiderivative to do, but sine squared is not a nice antiderivative. Let's take it over into the lab. Sine squared is 1 minus cosine squared. And I know that cosine squared is 1/2 1 plus cos 2 theta. Or 2 phi in this case. And so when I simplify this down all the way, I get 1/2 minus 1/2 cos 2 phi. I bring that back in. I could probably factor out that 1/2 a little bit. Let's see how this works out. 0 to 2 pi, 0 to pi over 2, 48 over 5, because this gets cut in half. 1 minus cos 2 phi, d theta. Now we are cooking. This is all just going to run down. I just have to be careful with this coefficient that's multiplying onto the outside. When I do, I'm going to get my antiderivative, 48/5 phi minus 24/5 sine 2 phi, because the 1/2 comes out from like an anti-chain rule thing going on here. Evaluated from 0 to pi over 2, d theta. Still keeping on. We're going to make it. This now is going to plug in that pi over 2, so I will get 24 pi over 5 minus sine of pi is 0. Sine of 0 is 0. This is 0. So I'm ready to go. It's just this constant. And again, these kind of things are not as surprising to me because this happens as we do these calculations. Don't be surprised when this starts to all shake out. Every step doesn't have to be terrible. It actually should be lightning and lightning and lightning and lightning and lightning until we get to the very end here. When I plug in that pi over 2, I get 48 pi squared over 5 for my final answer. And again, that is the divergence given this vector field across this hemisphere. And you won't know what any of those words mean till April. But you know how to do the calculation today. You don't know how to do the setup. You don't know what's going on in here, but you can do the calculation today.